So, playing video games, one frame at a time. This is my face, this is my name. I'm a senior software developer at a company called Factlines in Norway. And if you want to yell at me after this, this is my handle. I'm this name in most places, so you should be able to find me. If you want to yell at me. Some people like to do that, so you can totally do that too. I work for a company in Norway called Factlines. We deal with supply chain network tracking. It's very exciting, interesting business, but yeah, fun stuff. I like to start talks with some philosophy, some kind of hoity-toity, right? This kind of fancy, fun things. So people say doing nothing is impossible, but I do nothing every day. Kind of fits with the gamer mentality, right? That's Winnie the Pooh. I recommend looking up like Winnie the Pooh quotes and thinking of them as philosophers, because they're amazing. I've used Winnie the Pooh quotes for the past like 3 years as like intro quotes, and they're amazing. I love them. So, who is this person on stage? This is me when I was younger. I worked in air traffic control systems for many years, doing overflights and radar stuff and that kind of thing. I was in the gaming industry for 7 years. I'm in this photo, if you can find me. I promise, I'm there somewhere. I was a consultant in Norway for a couple of years, and I also do this kind of stuff where I yell at people for fun, like you lovely people. So, what is this talk about? So, a good way to describe this talk is it's a bit of silly fun, it's a bit of curiosity, and there is a real-life use case here that you might not have thought about. And you will be annoyed at me when I show you this real-life use case. I'm very sorry. It's also not an area that a lot of people explore. So this is not commonly this is not a thing people do regularly. So let's have fun with this. Oh yeah, there's going to be a bit of preamble here. Also, I did a talk just an hour ago, and I've done this talk before. That was way more serious than this one. Very serious. It was about how humans learn information. That was a talk I did just before this one. It's also online if you want to see it. And in that talk, I said this. Unfortunately, in this case, there's considerable evidence that in many situations, this strategy, which is the 1-hour lecture, is rather poor. A lecture may inspire, it might motivate, it might inform, but it rarely fulfills the principle for effective learning. It is certainly inadequate for developing high-level skills. We have known this since 1971. So, I cannot with good conscience, after making a talk like that, to then come here and try to teach you something. That's kind of hypocritical of me, right? So, I decided that my next talk is a fun talk, right? Let's have some fun. It's also Friday, right? Yeah, let's go. I see a lot of nodding heads. Good stuff. There's some audience participation, so hands in the air is fine. Okay, more preamble. Warning. I will do stuff to video games in this talk. If you are going to do similar stuff to video games, I'm pleased, and I'm asking nicely, please don't do this to only single-player, non-online games. And now I'm not responsible for anything you do. Cool. It's not crazy stuff, but I feel like I'm giving you enough tools that, yeah, I feel I need to add this warning. Okay? So, boring backstory. Playing video games is great fun, but I'm also a programmer, right? How can I marry these two things together? How on earth can programming and video games ever come together, right? Well, you can make games, but as you saw in the beginning, well, I did that. I did that for 7 years. I worked on games for 7 years. So, but what if there's another way, right? Well, games are just applications, right? I think so. What can we do to control these applications remotely? What are the different challenges that you will face when trying to interact with this complex software, right? And can some of this apply to interacting with other software, okay? And since the theme of this talk is video games, we have to have levels, right? We have to be on brand. Yes. So let's start on level 1, okay? So, what if the game we would like to play supports playing it programmatically right out the box, right? It's the easiest way. I would like to play games programmatically. What if the game just allows you to do that? So, Doom. Who here knows Doom? Or maybe, okay, who here doesn't know Doom? Okay, we have hands, good stuff. Then, Doom is a 1993 first-person shooter. And it kind of redefined a few aspects about video games. The look and feel of first-person shooters, some games were like working in that direction, but games going forwards looked at Doom because they were thought of as Doom clones and the first-person shooters after that. Online multiplayer, which is like 93. How do you have online multiplayer in 93? But yeah, Doom had online multiplayer. It was kind of a simple way to do it because every action was lockstep. Nothing was resolved until everybody on the network was resolved. So, but hey, it worked. 93. Game modification as well. Like you could go and mod the game and it's still being done to this day. And video game speedrunning, which is again an area not many people might think about. And we can't go over everything. In this talk, we will actually look at the last one, video game speedrunning. Because whenever there's a timer, this is psychology. Whenever there's a timer, there's always someone that tries to be the best, right? Because I can compare numbers. That's wonderful, right? And Doom is no exception. And they even taunt you with it. Because this is when you finish each level. You get a little screen, how you did, what you did in the game, how long it took you, and how long it took the developers. So if you were slower than the developers, they were like, you gotta be better than that, right? Also, a fun thing, you can see this, they got all the items in the level, they found all the secrets in the level, but they didn't kill any enemies, which is also, like, this is a very silly screenshot. But you can see, it took them 1 minute and 16 seconds. Cool, now we can compare. There was a timer. And as you can see, people are still playing, and they're still trying to get better. E1M1, which is episode 1, map 1, Hangar, Alexei Kamenev, 8 seconds in 2019. People are still trying to get better. I think one of the things they found with the first level, because it's so short, they found that if the enemies shoot you in the back, you get a little boost, right? They're thinking of that kind of stuff, of like, how can we manipulate all the little tiny things? Yeah, and you can see there's a file, E1M1 P897. Cool, and we can download these files, all right? But if we download these files, we'll notice they're actually pretty small. These are some other files, but notice they're pretty small. They're a few kilobytes. That's weird, right? How am I going to look at what this person is doing if it's a few kilobytes in size, right? The reason is these files only contain the inputs that the user did during each individual frame of the game. In frame number 104, they press this button. In frame number 106, they press this button, right? That's the only thing these files contain. There's nothing else there. Here's the header of the file, if you're curious. Okay, everybody remember? Good? No? It contains the version of the game, the skill level, any of the expansion packs, basically anything that might then modify what's going to come after that, right? And then each line, or each set of bytes, is what you did. I'm pressing forwards, backwards. I'm strafing. I'm turning. I'm interacting, doing some shooting a gun, opening a door, or whatever, right? And then during that frame, the first frame, we did this thing. During the next frame, we did the next thing, right? And there's an application called XDRE, or many other applications, where you can just look at it. You can watch it. So here, each of these are the lines for the demo. And then on the other side is the game. And you can just see the game moving. You can see all the parameters. I'm going back here, going forwards, forwards. So yeah, that's pretty cool. How can it do that? Well, this is possible because of one thing. Doom is deterministic. So this is a bit of the code. You don't have to read that code, it's just some code. Fun to have code on screen. Doom is a single-threaded application where every entity on the map that you are playing patiently waits their turn. Always, and always in the same order. I get to move, then some monster gets to move, then yada yada. Door gets to open, like it's always the same. Always in the same order. Some more code, if you want to look at some code. I love the indentation of this stuff. Int, and then I. Good stuff. Good stuff. I recommend, if you're curious, if you've never seen like video game source code, go look at video game source code. There's like the video game source code archive on GitHub. There's a bunch of like old games. It's very interesting to read because the formatting is wild and the comments are wilder. So yeah, I recommend it. But what about random? Some of you might know this. When they want to do something random, when any of the entities, I'm shooting, how much damage, if the monster is going to move towards me or whatever, anything random, if I want to do something random, I pick a number from this table. There's an index there at the bottom that says where are we in this array? Just an integer. And then if someone is asking for something random, they get the first number. Then the next entity will get 8. Third entity will get 109. Fourth entity will get 220. And when it overflows, it goes back to 0. So we just continue. So any kind of randomness, it's even like when you're shooting and the bullet hits the wall and there's like the smoke puff, that gets values from there, right? When the screen scrolls down, like this animation, that pulls from there. Right? So an index will increment it, and the next entity will get the next number. Good. So what if you wanted to take Doom and convert it to, let's say, for example, C++? Doom is written in C. So this is a fork, usually called source ports. Initially started by Jason Turner, and then continued on with Patricia Ross. Then I was dragged into that kind of fun. It's the idea that let's take Doom and convert some parts of it to C++. What kind of C++ things can we do to the source code? But the thing is, this is a pretty complex project. How can you move forwards with the code changes that you have done, knowing that whatever you did didn't break stuff, right? Well, you can try playing the game, right? The thing Patricia did when she was refactoring it, she would refactor something and it would compile, cool. And then she did some other refactoring, it would compile, and okay, cool. And I asked her, like, okay, and did you play the game? Like, no, I didn't play the game. I'm just refactoring. And then we checked it, and yeah, it had broken. Something had broken in what she did. So you could try playing the game. You could write unit tests, and we wrote some unit tests. Sure, we can do that. But we have the tool in our hands right now. So there's a thing called approval testing. Approval testing is a methodology where you focus on comparing the old known output of the code, whatever the output is, to the output of your new code. So you need somewhere to compare it. So think of it a little bit as a git diff. Your old code outputs something, okay, some numbers, some values, some stat screen or something, and then your new code outputs the same thing. Is it still okay? So this is very useful when you want to do a complete rewrite, or when you want to write it again when the old source code isn't known, right? You know how the application interacts, you know how it behaves, right? But you don't have the old code, so you can do approval testing. Old code did this, new code should do the same, right? So in Doom, you can give it a parameter where you say stat dump, it's called. So when you're done with a level, it will give you a little screen like this, which is the same screen as you saw before. How long did it take you? What was the power? How many kills, items, secrets, yada, yada, right? So if I play that demo file, so they're called demo files we had before, on the refactored version, I should get the exact same results. Is there an echo? I don't know if you... Okay, so it's just for me. Okay, no problem then. So if I play the demo file on the new version, like I have the old known code, I have the new one, I should get the exact same results, right? Another tidbit with this, the game doesn't actually need to render to the screen. So I think if you don't know for games are, you have the simulation of the world, then you have just a graphical representation of the game state. That's the only thing that's happening. So you have some state, some entities, where they are, what they're doing, and then you have the look of the game, right? We can add and modify some of the flags that Doom has, where you can run Doom in the terminal. Doom actually had support for this, but it didn't run like as fast as I wanted it to. So we can run Doom in the terminal with no graphics. It just runs a demo, gives me the stats output. This means that we do not need to run the game at a nice frame rate. We can just run it as fast as we can. Because I only care about the statistics output, because the simulation is the same. All right? putting one and one together so we can play the game using the known good version. We play it a bunch of times, have a bunch of good statistics outputs. We collect all those outputs into a file. We save those files and the demo files next to each other. Then, of course, some wonderful bash hacking. You don't need to read this. It's just doing a diff. We run the game, we get the new output, we diff it with the old output. So we're doing approval testing. This then means I can run Doom in GitHub Actions on all these versions, on all these operating systems. Here it is. You can see almost the bottom one. It's called demo check, the fourth from the bottom. Takes 0 seconds, even though it's running like 10 demos. One of them is like 6 minutes long, but since we're running it as fast as we can just do that. And that means that, and then for those who have played Doom, remember this little output? We actually, because the shareware version of the game you can share, so we have it in the GitHub itself, so we can use it there and run it in the GitHub Actions. And then that means, yeah. Then we can collect all of the stats output for a bunch of edge cases. And I got some help from the Doom community to find like, oh, if you do this thing here, like 2 of the enemies will fight each other and then they'll have some fun. Like find a bunch of these weird edge cases, and then they are part of our testing suite. So that means that you can go and refactor. Be at least more comfortable in knowing that what you didn't break anything, right? Okay, cool. Are we on time? Yes, good. Should we level up? Level 2. What if the game you want to play doesn't have the support that Doom does? Bejeweled. So who knows Bejeweled? Okay, about half the room. Good. I recommend this game, very addicting. Or Bejeweled, perhaps the most insanely addictive puzzle game ever, as they say on the box. Correct. So, Bejeweled 3 is a match 3 game. Great name for that kind of game. You pick a gem, you move it left or right or up or down, and you can you create a 3 of a kind. You can also join 4 of a kind or different kind of shapes, and there are all sorts of fun things you can join together. When the match happens, the gems go away, and then the space is filled by the other gems, they fall down. Or if it's like a special gem, they might blow up and other fancy effects, right? So we would like to play Bejeweled 3 by ourselves, like the program play the game. So what we do is, we first find out what gem is where. Then we pick a good move, once we know where every gem is, and we move that gem, right? Cool. Which one of these do you think is the trickiest one? There's one of these that's still causing me issues, but yeah. And then, yeah, you loop around. The project, C++, CMake, reset package, and OpenCV. Just a simple little setup. It's actually not that much code. For those who don't know, OpenCV is an image processing library. I initially used it to do some like color detection, but then like it went a bit further because I wanted the pixels, I wanted the graphics from the screen itself. So step 1, what gem is where? Another note, if you're doing this and you're playing with the game is actually this big. You can play it in like a fancy mode where it has like more special graphics effects, but when I was doing this, the game is 800 by 600. So for your convenience, I will make it big. The game board is it's fixed resolution, and each cell is 64 by 64 pixels, which is a wonderful round number. The offset of the board, where it starts, is 261 by 37. So that's where the actual game board starts. So this means like I know where each box is. So then this is just an array. It's just an array of some items. Good. But how do I know that that is the green one, right? Because I have the array, I know how big it is. I need to then fill it in with the information. What I use is just characters, so G for green, R for red, that kind of stuff. So I need to create this array for each possible state. So I started simple, because with any problem, you should just let's look at the simplest most thing we can do. I just took the center pixel. What is the color value of the center pixel of that gem? If it is roughly the greenish thing that I think it is, then that's green. That works until you click on it. Because of course for the game, it's wonderful. I don't know how many you see. It spins. which is, I mean, great. It's wonderful for the game. It's not so good for me, right? But of course, I am the important bit of this information, right? But that's cool. Okay. So the center pixel then doesn't work. Maybe like a range of greens. But again, no, that doesn't work because, yeah, there's like this shiny thing that happens that is kind of similar with other shiny values. So yeah, it doesn't work. So since I had OpenCV to grab the screen, grab the pixels, let's use OpenCV because they have a thing called template matching. So you give it a template, an image that you would then want to find in a bigger image. So here's Messi having some fun playing football. I would like to find this face of Messi in a bigger image. And since this is a statistical method, we'll have like a range of values from 0 to 255. And you can see that if the mouse is here, here is the brightest bit of pixels. And so the algorithm thinks like, yeah, it's most likely there. That's where Messi's face is. Like this is kind of white because like maybe Messi's face is there. It's not there, but like, again, it's statistics. And they have a bunch of coefficients and all that kind of fun stuff. So yeah, I thought like, hey, I have these shapes. I have these wonderful shapes. And I have these colors, right? So this is perfect, right? So I created a bunch of templates. These are not templates, but they actually had like they had a transparent background, but it doesn't matter much. So I have a game, I have my little application, and then I have the algorithm to find the template matching, and then I find all the red ones. Where are all the red ones? Who can see the problem? Give me a hand for the problem. Yeah? Yeah, why? What is that? So, because template matching is very sensitive to things that are not in the template, I had this open for a little while I was playing with it, and the game, very helpfully, was trying to give me a hint. I'm like, hey, if you move this yellow one, you'll get a match. But the hint is like this arrow, and it goes into the red, so the template matching breaks, right? This is not great. But we have this threshold, so we can just mess with the threshold, find another value. So I do that. And again, you can see the problem. It's now fine because this orange one is like a special one because joined some of them together. It thinks it's red, which of course it's not. It really thinks it's red because it can match multiple times. So you can like match this pixel, but if you shift it by one pixel, try to match it again. So you can do like multiple matching. And it really thought that this was red, which of course it's not. So yeah, this doesn't work. And one of the reasons why it doesn't work is a lot of these algorithms take the templates and make them black and white. That's my main advantage. That's my main thing is they are different color. So my thought is like going forwards, this is not going to work. Even with the perfect algorithm and the perfect whatever, tweaking of the values, there's going to be a case because I'm losing the main thing here, right? Let's go then back to the idea of color. So what can we do? Let's not check for the RGB value of the gem. Let's look for the hue. So for those who know, HSV is another way of looking at color, and then hue is just a wheel. So you have a direction of where you are on the color wheel. Think of it like a vector. If you're green, you're pointing in that direction, right? And also, I grab a 32 by 32 area of the center of the gem, and I get the average color of that area. So even if it's spinning, it will vary, but not by much. And if it has the special effects, it's still kind of green or still kind of orange, right? And some of the special effects are on the outside, so I'm safe from them as well. There's one where it's on fire, so that's fine. And then I check against the hue, saturation, and value, and not the RGB. And I can see that this green is roughly there, right? Okay. So I then went and played the game for a little while and checked the hue, saturation, and basically the hue value of every single gem in every kind of combination, on fire, shiny, whatever. And I made a map of where they overlap. So the blue of the hue value of the blue is usually isolated. The hue value of the green is pretty isolated. The orange and the red, the orange and the yellow can kind of overlap in some cases. And you can see the purple and the red one, which are the top one. So this one here is kind of overlapping into the red one. But what I can do also is I don't only have to use the hue, I can also use the RGB as well to help disambiguate. Then I wrote the world's most complicated function, where I take in the hue and the red, green, blue, I extract those out, and then I ask, are you roughly this value? Then you are blue. Are you roughly this? Then you are green, right? This is I cut away some of this for the slides. I'm also using the color, the RGB, and all that stuff. But yeah, once I have this, I can basically cut out. If you are within this range, I know you're blue. If you're within this range, I know you're green, right? And et cetera, et cetera. And this works. Sometimes it will like mess up, but generally, yeah, this gives me like 90-something% of the values. So this is great. That was step one. Step two is pick a good move. So now we know where everything is. We know the state of the world. I need to do something, right? So what does it mean to be a good move in this game? Yes. Initially, I was thinking some cool AI, yada, yada, but after the whole color fiasco, like, let's start simple and see if that's good enough, right? And it was. You can, of course, do more things, but to get it working, let's start with something simple. So, again, I played the game just a little bit. I still haven't recommended it, but we'll get to that at some point. And I had an idea. There aren't actually that many moves in the game. Not really. Like in the span of like chess or that kind of stuff. Like in this game, no, not that many. Can we just map them out? Just have a list of them? So I did that. So I made a little format. So the idea is you have CXBA. So you want to have A, B, C, and there's some X in the way. An example is this. The yellow is in the way. I want the C to be next to the B. Okay? And this is the pattern I want to look for. So then I have the values. So, and I think of A as the origin, and then B is -1, and then C is -3. And then it's a horizontal 3i, and the solution is to take always the last one in the points and do what to it? It's the solution you have to do to it. So of the -3, I want to +1 to it, then it'll be a -2, they will be next to each other. That's the idea I want to do, because I want to find this pattern somewhere on the board where I find these two oranges in 0, -1, -3, and then perform the solution on the C. I then give it an idea, give it a value. This is a value of 1, because this is like a very common one, but if it's like more gems and more points, then that's a higher value. Put them in a list of patterns. Here's a more complicated one. You have AP, ET, and then the C is there. This is kind of a corner join. So the red one is coming in. So you see the last one is the pushback of 1,2, and the solution is to do a -1 on it, so it's the same as the A. So now we have a solution for it. And I give it a value of 3 because I want, if I would have a board and I would detect this plus some other stuff, I want this, right? This is the one I want. There's 32 of them. I did not find more. So that's also an odd number, right? The programmer brain is like, wait, 32? Why? So if someone wants to research why, go ahead, have fun. I stopped at, it's like, interesting, moving on. Okay, so now we know moves, but which of them should we pick? Well, if it's a higher value, so what I do is basically I take the board and say, give me all the moves. What is everything I can do on the current board right now? And then I sort it by the value. So the highest value of the current available moves is the first one in a vector. But what if all of them have the same value? So like here are 2 of the 3 combo ones. The green one and the purple one on the bottom. So they combo 3 together. So what if that happens, right? Which one should I pick? Well, I pick the lowest one on the board, because when you connect them together, the stack will fall down and you'll have more incidental connections that will happen when you do that. If you do this on the top one, only 2 or 3 of them will fall down. If you do it on the bottom one, you'll have like 7, 8 of them that might incidentally match, right? So that's, and if there are 2 on the same line, I just pick whatever it happens to be the first one, right? So then step 3, let's move that gem, which is the simplest way, the simplest thing in this whole thing, because Windows has an SDK. They have the mouse input SDK. So if you want to play with that, please do. I want the function that's basically this, because now I know where they are and I know what move I want to do, because I know what C I want to move in what direction. So I know a function where I'm starting from and where I want to move to. Cool. I need a little helper function because I want to do things in absolute, because I have the screen and I want to convert from the absolute screen to the game screen, etc. So I have a little conversion function. This funny division that's there. It's a weird one. In absolute screen, the screen is really big, so you have to find out the system and get the system metrics to get the scaling of the window. So it works with multiple scalings. Yeah. Anyway, it's a weird function. And this might look much, and you don't have to read all of this, but I'm just showing that I call that function to get the actual value. I create an input that says, go to that position on the screen. I click, I get the end absolute position, I move to it, I release, right? So where are we gonna go? Let's go there, click. Where we're gonna end up, let's go there, release. That's it, right? So, what's a demo? Has everybody prayed to the demo gods, right? I have 2 demos, so it's gonna be fun. So all this time I have the game running. It's been running in the background. Let's go here. And I have the code. Let's see. No, you need to start the game first. So here's a fun thing. When you're creating applications that mess with mouse movement, you're kind of stuck. Because it's, which is fun. Luckily, I only run it like 25 times, so it's not much. It doesn't bother me much. Okay, here we have a game board, go, and let's go. Oops. There you go. Replace, have some fun. So, there's a couple of things that I noticed when developing this. Bejeweled doesn't lock the board. So, I have actually a 600 millisecond sleep on this whole thing. Oh yeah, I finished the level. Level 2. Oh, is it over? It's over. Yay! So we can increase the moves. We can lower the sleep. And let's see if things break, right? Because what can happen is it's too good. So when it matches, things are falling down. It finds matches in the air and tries to do them. So you might see it be a little bit confused when we do this. Let's do a build, have some fun. Build started, good stuff. Let's play. Yeah. So you see sometimes it will do a move that doesn't make sense, like go back and forth. That's because it thought there was something there when it wasn't something there. And then so yeah, that's kind of fun. So I've been really good at Bejeweled. I mean, the game is a fun game. All right. How are we on? Good. Okay. So, cool. Let's level up, right? Yes, your question. Oh, you want the thing? We can do the thing. So this kind of method of doing it, it's real time, basically. The same frame rate as the game. It's a few milliseconds to do the whole thing. So you're screenshotting, doing the image analysis, doing all this thing. The version that has the template matching, that was like 500 millisecond delay between actions. So that was another like negative part of that. So let's do, let's remove the sleep. And we need to, I don't know how many, it might be really fast. And might not make any sense because it will just finish immediately and do a bunch of moves. So let's see. So yeah. So this loop that it happens, we can make it go a little longer. We have time. Let's do. So you might see it happen, like do the whole looping of the thing. That means that it moved it down, and during the move down, there was a match. So it did the other. So it's trying to double match, kind of, if you think of it that way. Build it on. Try again. Yeah. Yeah, the bottom there is really interesting. Oh, you got it. There you go. There you go. So yeah, it's pretty fast. Thank you.
The game had no animations at all. How fast your program like?
I think this is a case of like the next step in this kind of thing would be to write a game of Bejeweled that has like instant match states that has no animations. So like make let's say a web version of the game where you can like instantly match things and it would resolve the board immediately. But then you can have a player that immediately just does it and plays the game as fast as you can. Yeah. Yes. And otherwise, EA, you can call me and give me the source code. I know you're not using this game much, so yes. All right, should we level up? Yeah, but this is going to go incrementally a bit more crazy. So, what if the game has none of this? Right? It's not doesn't support it. There's no simple game state. Like it doesn't have a game board we can play with. So, who knows this game? Yeah, this is always I get like two hands usually when I do this talk. Instead of like Bejeweled, I get half the room. With this game, it's like two people. There's the game called VV. I'm going to call it V for you. It's a platforming game where the only thing you can do is, so you can't jump, but you can flip the gravity. So that's the gimmick of the game. It kind of looks like this. It's like a demo level. Of course, spikes are bad. These blocks are temporary. You want to find these trinkets. And yeah, so the idea is to flip the gravity and yeah, move around. So it's pretty fast paced. You need to have like very delicate movement, like pixels matter, right? So it does not have any built-in support for giving the game the inputs. It does not have a simple state. Like from a game designer's point of view, it does. For our point of view, it doesn't, right? It's pretty fast-paced and you need to be pretty accurate with the movements. So I thought I was going to be hacker man, right? I'm going to do some cool hacking to the game. What ended up happening, I was more this guy. So yeah. Before I continue, there's one concept that I need to mention, which is the game loop, because it kind of matters in this case. So games are applications like any other, but many games have a certain structure that they all share. They get the input from the user, they update the state, whatever the state is, and then they take the state and they draw it. That's the thing they do, and you go again and again and again. How they do that is very, very like varied, and there's a lot of caveats to this. Getting the input from the user might be different based on game. Updating the state can be actually pretty complicated. You might do partial updates. You might offload it to a thread. You might like do updates in multiple steps. And also drawing can be like, you take the state and you just send it off and you don't care about it. And then you're working on the new state. So that can also be offloaded. So it can be pretty tricky. But to make this a little simpler for our project, I picked V because it has a few benefits for us. So again, initialize, we process the input, we update the game state, we draw the game state, we go back up. This is often called a frame. Some people want to call the bottom part a frame. I like to call the whole thing a frame. If you want to, this involves in rendering the frame. This is incidental, like the time it takes doesn't matter too much. And here, the updating of the same state, how long does it take? It depends. And drawing, it depends. But if you're in a 60 FPS game, you have 16 milliseconds to do all this. So like imagine doing all the work that you're doing to calculate the next frame, and you have 16 milliseconds to work with. So that's kind of the big problem that game programmers have, is that restriction. So often you will batch things out because you don't have the full 16 milliseconds. Some games have the idea that this should be at least once per 16 milliseconds. So the game state is being updated, and then we draw as often as we can. Let's just try to draw as often as we can. So code example, let's get some initial time data, an infinite loop. What time is it now? Then I have a thing called accumulator. So I'm accumulating how much time has passed in increments of whatever the increments are. I have some function that will take the input. And then I will ask, do I owe you a game update? Because one accumulation might be 1 millisecond, the next one 2, yada, yada. Once we hit 16 milliseconds, 16.6 milliseconds, I owe you a game state update. right? And then I update the game state. I decrement the accumulator, so I've now paid that debt, and then I draw. So if I don't owe you an update of the game state, I don't update the game state. If I'm in massive debt, then I will update the game state many times. But I will always then try to draw as many times as I can. And this is just one loop. There are many different loops. They have pros and cons and that kind of thing. With this one, for example, if you implement an application using this and you click the taskbar, like the status bar on the top, and you drag it around, the application freezes. And then when you let go, you've owed a bunch of game state updates. So you will do that loop like 100 times or something, and then draw once. So yeah. The thing I said, sure. So V actually has a few advantages, and it's why I picked this for this project. It's open source, so you can just go and check. This is the actual game loop or part of it. You don't have to read. The important part here is it's single-threaded as well, and it has customization where if I run it in 30 FPS mode, you see line 4, if game mode over 30. What it's doing then is it does one input check, it does one game state update, and does one draw, always. Then it goes back to one input, one update, one draw. And that was an important part for this project, because if they aren't in sequence, it kind of makes it a little trickier. So here's my devious plan. I will launch the game as a paused child process of a loader. So I have some sort of loader application, and I will then spawn the game as a child process of myself. And then I will inject a DLL into that child process. And that's my code. So I have the game and the DLL in there. I will then hook the function that creates a DirectX device, which is the one the game uses to draw to the screen. I will get the address of that device. I will intercept the game's draw call to call my draw call first, my function first. And before we actually draw something to the screen, I will use the Windows Input API to send my keyboard inputs, the keyboard inputs I would like, right? Because I know once the draw call has finished, the next thing that will happen is the input check. So then the game will check for the inputs, which is the stuff that I sent in the last draw call. Then we go back out, update the game state, update the draw call. But before we draw, call my stuff. I intercept. I send in my keyboard inputs, and we go back up, right? So here is where I hook, and I send the inputs. And you might ask, couldn't you hook there as well before we actually do the checks for the inputs? And you can, but the thing is, if we do it in the draw, we can also draw debug UI, which is really nice. So when you're working with this, you can have something to look at. And that's what I did as well. And some of you might think, wait, that's illegal. Why are you, you're manipulating the application? And Microsoft agrees. Operation did not complete successfully because the file contains a virus or potentially unwanted software. Because it is. That's what we're doing. And that's what some viruses do. But luckily, this only happens in release mode. If I do this in debug mode, Windows doesn't care. So it works. So what you see is debug mode version of this. There is another library, hooking library, where apparently it does work, but I haven't converted it over because it doesn't matter much for this talk. But if you want to play with this, just note that you might have to convert to another loading library or fool Windows. I don't know. Maybe talk to them if they're here. Which is funny because the library I'm using is from Microsoft. So I'm using Microsoft Research Detours package, which is usually just called detours. Detours, the idea is to, detour function calls. If someone else is calling a function, they can call your function first. And this is a library that will help you. It does look like a lot of boilerplate that you have to work with when you use this, but you're saving so much more. It's so much more that you have to write for this kind of stuff. For those who haven't played around with this kind of stuff, this is the idea. We need a pointer to their function, where that function is in memory. Then we have our function that will be called instead. And inside of our function, we call their function, but we can also do work before or after, right? So at some point, we will call whatever their function is because, hey, we want to be nice. right, good. But we might do some work as well, right? So from their point of view, everything is fine. And if you use applications like OBS or Fraps or any kind of like screen sharing application, a lot of them are doing something like this. Especially, I think OBS is doing a lot of this kind of stuff. Also, if you're screen sharing a Discord, that kind of thing as well, they will hook into these kind of things. For those who haven't done DLL stuff, this is a DLL main. The reason why there's a DLL main and not a regular main is that DLL mains can be called many times. So, and it's a reason why they're being called. So I can initialize detours, and then I have the reason for why I'm being called. Either I'm being attached to a process or I'm being detached from a process. And then I can do some stuff, right? What I'm doing there doesn't matter much, but the idea with a DLL main is it's being called many times and why you're being called, right? And of course, the first thing you do is, hasn't someone done this before? And yeah, of course, people have done this before. But I wanted a nice, simple example for this kind of stuff. So the game is using DirectX 9, which is pretty old. So I need some code to hook into what, there's a function called endScene. And the endScene function is the function that, like, the game has set everything up. They are ready with their game state. They have basically set up the commands that need to be sent to the graphics card, and they call endScene. And once they call endScene, then that's being sent out, and that's the thing that's being drawn, right? So I want to hook into the endScene function because that's always the last thing being called. And this from Tom Gascoigne, if you're watching, hi. Your code example from 12 years ago was really nice. And it formed the basis to my project. And I love his last commit message, which is, whoops, forgot to commit a new class. Like, who hasn't, right? We all relate to that. So I have a function where I have the name of the DLL that I would like to hook. Then it's the process of the game that I would like to start. So this is my loader. So I have the DLL I would like to inject, and I have the process that I would like to inject it into, and then I'm calling the detour create process with DLL. And I'm creating it suspended, as you see in line 2. So the game starts, the application starts, but it's not doing anything. Just to make sure, good. And then at some point, it will resume, so the game gets to go, but after we have done all our work. So we get to do our work first, and then the game gets to do its work. And then we just wait for the game to quit. And once the game quits, we quit. And then some error messages if we want to have some. And here's my DLL main. It's pretty simple. The only thing I care about is when I touch, because I don't care about the detach. I don't need to do anything. And I call a function called hook create device. And then I don't care about the rest. So the only thing I care about is that hook create device, and I will call that. You'll see this message box thing. If you're doing DLL stuff, and sometimes debugging can be hard. You can't actually debug and put like breakpoints in that. Message box A is kind of the printf of the DLL world, because you'll get this. So you know you were okay. Like, you get a little message box. So initial experiments, they worked. So here's the trick. Because at some point, once the game starts, the game is going to create the graphics device. And I would like them to call my function when they create the graphics device. So I hook the create graphics device. That's the main function that I hook in this whole thing. But I need to know what that function is. I need to know what function they're going to call so I can hook it. So I create the device on my own, and I don't actually care about the device, because what I want to do is I want to get the virtual function table. So this is a very beautiful cast that's happening here. But what it's basically doing is I have this object, and usually if you have objects like this, they have a function, basically virtual function table above in memory. And if I do this cast, I will actually have a pointer to the virtual table, not the object itself. And then I just release the object. So now I have this object. But the thing is, this object is VM protected. That's from Windows. So I have a function that will un-VM protect the thing. I will give it the address of the function, and I know where it is, the offset of the function in that object. So it's 16 bytes in for the create device, 42 bytes in for the endScene. That's just known from that interface. So it's this big. I want to make it rewritable. And this is the code I want to run, which is the lambda. once it is read-writable. So once it's rewritable, I run this code, and then once this code is done being run, it's no longer rewritable. So it's kind of a nice class for that. And what I do is I say I store the original create device function, and then in that place, I put my create device function. So I know the memory of the old one, and then I put mine. So now, whenever someone creates a DirectX device, they will call my function. Okay? So let's do a summary, because I've been doing a lot of things. So I spawned the game process paused. I attached our DLL, which is just an application, to the game process. I hooked the create device, so the game is going to call create device at some point. And then the next thing is, once the game calls create device, I now have in my hands the device that they will use. And because I have the actual object, the instance of the device that they will use, I can find out what is the end scene function that they will call, because that is dynamic. So this is why I needed to get that. So this is the create device hook. So this is the function they will call when they create the device. I will create a device, which is the original function, which is why I stored it. And I will just pass in whatever arguments they gave me. Again, message box, great if any errors occur. And then again, I use the protect class to find out, this is putting back the create device. So I'm being a good boy, putting back the original create device. And then I get the virtual function table for this new object that was created. This is the DirectX object. And I find out the end scene, and I do the same thing. I store the original end scene, and then I put my end scene function. This means now that every time the game calls end scene, they will get a message box saying game rendering hooked, because I had a message box in that. Funny thing is, the game actually has 3% loaded before it actually starts. I don't know why, but it's fun. But yeah, we have success. Now, every time the game is being rendered, they're calling my function, which will then just pop up a message box, but that's okay. Which means I can create this function, which is my end scene function, which just calls the original end scene function, because again, I'm being a good boy. I will count the frames with a static variable, how many frames have, basically how often I've been called. Then I can say, on frame 1, press the spacebar button. On frame 2, release the spacebar button. Right? This works. Because the game, when you start it, and the game has launched, if you press space and release, it will go to the menu immediately. So when you do this, the game goes to the menu. Which means I can create a little bit more complicated version. You don't have to read the whole part of it. It's a similar thing, but I will load data from a text file first, which looks like this. If I have a big S, I will press spacebar. I have a little s, I will release spacebar. I have a big D, I will press the D button. A little d, I will release the D button. Which means that if I am on frame 2, I press the spacebar button. If I'm on frame 3, I release the spacebar button. Then I can just create a file that will perfectly recreate the gameplay that I want. Okay? What's a demo? Yeah? Yeah. Demos are always fun. So, here's the game. Playing around, moving. Again, I'm not. Oh. And how I created these, you can see in the top corner, there's like a frame counter and also how many milliseconds, and there's like a little debug UI there at the top. And what I can do, if I launch it again, I can say, oops, play at 100 millisecond delay, or play at a 1 second delay. So I fulfilled the talk of the title, playing games 1 frame at a time, because I also have the left, right, and the spacebar button here. And this is how I created the file. I saw on frame 146, I press the spacebar button. And then I write that into the file, press S on 146. And then I play it again and try it out. So incrementally make this little file. Let's see. I need to close this. So I can do some tricky things. Oops. Get. So let's maybe not pause. Let's play this a bit slowly. So this is a bit trickier interface. So there's a thing in games called coyote time, which means that once you've left the platform you're on, and you're basically supposed to fall down, you can still jump for like a few frames after that. So, oh, okay, I stood on the edge, and then I will go up there to the corner. I want to jump, and then I'm off the platform, but I couldn't jump. And then the big one, the fun one, I'm on that platform, goes down, I press space. So this is usually used in games because if it were perfect like that, it will feel weird when you're running up towards a platform and jumping, because humans aren't perfect. They will usually like slightly leave the platform and then they can jump, right? So games usually have a thing called coyote time, where you're allowed to be off the platform for a few. Who knows why it's called coyote time? Yeah, from the Roadrunner cartoons, where he leaves the cliff, and it's not until he looks down he realizes that he's going to fall down. And then we can get the trinket. I also, for those who played the game, you should know that these trinkets are part of the save file. But in a demo, I can always catch them again and again, just for demo purposes. That is because also in this thing, in this loader, I'm overriding the save file. I have the original save file, and anytime I play it, I overwrite the save file so I can do the thing again and again. And just for having fun, so who had played the game? We're here at the... Yeah? So there's a challenge in the game where, because you can't jump, you have to reverse the gravity. That means that if the wall just keeps going up, you also keep going up. So there's a challenge where there's one tiny block and there's a trinket on the other side. And instead of, because you can't jump, you have to go all the way up and then all the way down, and there's spikes everywhere. So that's the hardest challenge in the game. And yeah. Go all the way down again, and then, so you can see there was a tiny little box there. So you can't jump, but you have to go all the way up and then all the way back down. So that's usually what people find like the hardest. It's called Veni Vidi Vici, and you can see, like, play it again. The name of the map, things, Veni Vidi Vici, and then whoop, yeah. Fun stuff. There's also like fun people who like go all the way up and all the way back down and land on the other side. Like, oh, that's kind of a fun thing. All right, we're getting near the end. Are we? Yeah, we're good. We're good. All right. So, summary: games are neat, right? Yeah, it's fun to play with them programmatically. And when you have an application where you don't have the source code to, there's still ways to automatically interact with it, right? You would agree? Yeah? AKA, yes, you can still test your legacy app. Write more tests. This has been a testing talk. Right? And I've shown you, like, if you have this application, it's complex. It's like, oh, we can't test it because it's so complex or has the UI thing. Like, no, you can do things. You don't have to go all this way, but yes, you can write tests. And so for those who are curious about this kind of stuff, there is a community for it's called tool-assisted speedruns, where people are playing games using tools. They are way better than me. Like, if you think I'm interesting, then I'm 1% of whatever they're doing. Like, people are writing emulators, and within the emulator, they're doing the whole thing, right? So there's a website called Task Videos, or if you just look up tool-assisted speedruns, you'll find a lot of people. It's a very big and interesting community. They play all these kinds of consoles and all these kinds of things, and yeah. If you're interested about the Doom thing, it's called the Doom Speed Demo Archive. I got a lot of help from them. A bunch of the edge cases I had were from there. Here's some URLs. It's called www.hook or Visual Player on my repo. The Doom one is on Patricia's, if you're interested in that one, called CPP Doom. And that's my face again. Thank you. So, any questions, thoughts, comments, angry rants, bad jokes? Yeah? Thank you. Thank you very much. I think it's a Friday mood, yeah? No, I haven't. Oh, I have another project that I can't talk about yet, but that might be another talk. But it's using one of the games I have there before. So yeah, hopefully it will be a talk. It'll be fun. So yeah.
Have you considered putting any more programmatic behind the tool one, or this tool is flaming and I know I can get some more points versus?
Yeah. So have I put any more work in the Bejeweled one? No. The interesting thing that I had with the Bejeweled one was just to get it working. I've had some comments on Bejeweled, for example, with the solutions, like what move am I picking, where people have suggested using the min-max algorithms to find out like, which one would I, because we know what points, because even if it's a 3 match, if one of them is on fire, that's actually a better 3 match than another one, right? And you can also look a few moves ahead, saying like, hey, these are the ones that I know about. If I do this one move that's actually not great, even though I have like a 4 move over here and I want to do a 3 move, if I do this 3 move, I'm lining up other things. So it's actually then more points. And then you're into like this min-maxing and looking ahead into the future. But then you always have the uncertainty of like the randomness coming down from the sky. And there's one thing I think I know about the randomness is it will never be solved. Like the things you're getting from the sky, like unknown, will never be like 3 together. But it might match with things coming in like incidentally. So like there are some things you can learn about that. So yeah, take the code, play with it, and yeah, make it yours if you want to have fun with it, and make it for other games as well. It's kind of fun of like how can we mess with this, right? That'd be nice. All right, then have a happy Friday.